So I'm going to pick back up here. So again, if we put that in equation form, most of the most of the problems this week are going to involve kinetic and potential energy. And so we're going to look at the total energy of the system. Initial is going to equal the total energy of the system final. And we can write that using an equation as 1 half mv squared plus mgh initial equals 1 half mv final squared plus mgh final. And again, this side is the ending energy of the system. This side is the initial energy of the system. We could add spring energy, but for the first part, we're not going to. So for the problems this week, we don't have it. And I think, again, the big idea we're going to have is the total energy of a system is always, it's the sum of all the types. And that total energy for the system always stays the same. So that's our intro. I have one example that we can kind of do. The example is a ball. A 7-kilogram ball is thrown up at a speed of 40 meters per second. So we're going to start there. We're going to draw a sketch. We're going to find what is the maximum kinetic energy of the ball and where is that? What is the maximum potential energy of the ball and where is that? And then the last question is how high does the ball reach? So it's being covered up right now, but we'll see that. So for a sketch, we want to kind of show initially we throw the ball up. So once the ball leaves our hand, it's kind of like if we shoot something up in the air, it's going to have the biggest velocity initially. As it goes up, gravity is going to slow down the ball and the velocity is going to decrease. As the velocity decreases, it's losing kinetic, but energy can't be lost. Some other type of energy, which is potential, is increasing. So on the way up, the ball is losing kinetic energy and gaining potential. So it has, when it reaches the top, it comes to a brief stop for a moment before it starts to fall back down. At the top, you can see we've said that it has the maximum potential energy, and it actually has no kinetic energy at that very top spot. As it starts to fall back down, it's going to gain kinetic energy, so it's going to speed up. So our kinetic energy is going to increase and our potential energy is going to decrease. And then if we call this bottom part again 0, right before it goes back in the hand, it's going to have it'll be moving the fastest. And again, if we ignore air resistance, whatever speed it comes up with is the speed it's going to come back down with. And that's, if you've ever heard, people shooting off guns in the air, they follow the same idea. There is air resistance, so it does decrease some of the energy in the bullet, but it can come back down and it can damage people and things. So that's why that's a concern. So if we do the math, what is the maximum kinetic energy? So we have a 7-kilogram ball that's thrown up at a speed of 40 meters per second. That's just a simple calculation, 1 half mv squared. If we do the math, the energy for this system will be 5,600 joules. The important thing to understand is that the energy of this system is always, at any point in time, is always going to have the same value of 5,600 joules. So once you find the energy at one point, it's going to be true for all points in the problem. And so here, now we're solving part 3, where what is the potential energy at the top? I don't really have to do a calculation. So we're finding potential at the top. If I know that kinetic energy, it's all kinetic at the bottom, and I know it's all potential at the top, those two numbers have to be the same. So we can just set 5,600 initial equals to 5,600 final. And again, at any point in time, the total energy of the system is going to be that 5,600. And then mathematically, how do I find the height at the top? And this is a common calculation. We know the energy total in the system is 5,600. We set that equal to mgh, and we solve for the height at the top, and we get 80 meters if we do that calculation. And again, we're ignoring air resistance, so all of the kinetic energy is transferred to potential. So that's this problem. We have another problem, and then I do what is the speed of the ball halfway down. So this one was just an extra question. At halfway down,